Have you ever wondered how scientists can say with absolute confidence that one thing causes another? Not just that they're connected, but that A directly makes B happen? Well, that right there is a special power of the experimental method. And today we're going to break down exactly how it works. All right, let's jump right in. So to really get a handle on this, we're going to look at a real-world example. Some researchers in the UK wanted to answer a pretty intense question. Does being exposed to a Barbie doll, with its famously impossible proportions, actually cause young girls to feel bad about their own bodies? I mean, that's a huge question, right? And to answer it, you've got to be super careful. So how in the world do you even start to test something like that? Well, these researchers, Dittmar, Halliwell, and Ive, they cooked up this really clever experiment. The whole point was to isolate that one single thing they wanted to test, the Barbie image, and see what effect it had all on its own. And the real genius here is how simple and clean the process was. They brought in a bunch of little girls, around 5 or 6 years old, and then randomly split them into 3 groups. Every single girl listened to the exact same story, but, and here's the key, the pictures in their books were different. Afterwards, the researchers measured how the girls felt about their bodies. This simple setup, it's the key to everything. Okay, so in every experiment, there's this one thing the scientist messes with on purpose. That's called the independent variable. In this study, it was the pictures in the book. One group saw pictures of Barbie. Another group saw pictures of the Emmy doll, which is designed with much more realistic average body proportions. And the third group? They saw neutral pictures of things like balloons and storefronts, no human bodies at all. And then, of course, you have to measure the effect of that change. That's your dependent variable. In this case, it was something they called a body shape dissatisfaction score. Basically, they showed the girls a bunch of drawings of different body shapes and asked them which one looks like you and which one do you wish you looked like. The gap between those two answers, that became their score. Okay, so we've got our setup, but how does this simple design let us talk about cause and effect? Well, it all comes down to one absolutely critical concept: control. This is the secret sauce that makes experiments so incredibly powerful.
This quote really hits the nail on the head. Control isn't just one thing, it's a whole toolkit of techniques. They all work together to rule out every other possible explanation for your results, so you can be pretty darn sure that the one thing you changed is what caused the one thing you measured.
And these techniques, they really come down to 3 main pillars: manipulation, holding conditions constant, and balancing. Let's use our Barbie study to break down each one.
First up, manipulation. This is the active ingredient, right? The researchers didn't just find girls who already played with Barbies and observe them. No, they actively manipulated which images these girls were exposed to. Creating those other 2 groups, the Emmy doll and the neutral objects, was absolutely essential. Without them, you'd have nothing to compare the Barbie group to.
Next, and this is just as critical, is holding conditions constant. The researchers had to be certain that the only thing that was different between the 3 groups was the picture book. So the story they heard, the instructions they got, the room they were in, the questions they were asked, all of it had to be completely identical. This is how you prevent other factors from muddying the waters.
See, if you don't keep everything else the same, you run into a huge problem called confounding. For instance, imagine if the Barbie group heard a story about being skinny and popular but the other groups didn't. Then you'd have no idea if your results came from the pictures or the story. Your whole experiment would be worthless, totally uninterpretable. And that brings us to our third pillar, balancing. And the magic tool for this is random assignment. Think about it. All the little girls in the study are unique, right? They've got different personalities, different family backgrounds, different levels of self-esteem to begin with. By assigning them to the groups completely at random, you make sure all those individual differences get spread out evenly. It's literally like shuffling a deck of cards to make sure one player doesn't get all the aces. Now, this whole system of control is incredibly robust. But even the most perfectly designed experiments can run into trouble. Researchers always have to be on the lookout for things that could undermine their results. For example, a really common issue is, what happens if people just drop out of the study halfway through? This is called subject loss, and believe me, it can be a much bigger deal than it sounds. So, you've got to know there are actually 2 types of subject loss. The first is mechanical loss. That's when someone leaves for a random reason, like the computer crashes or the researcher makes a mistake. It's annoying, for sure, but it probably won't skew your results. But selective loss? Oh, that is a huge, huge problem. That's when people drop out for a reason that's actually related to the study itself, and it can completely wreck that beautiful balance you created with random assignment. Just picture this, a study testing some new, super intense fitness program. Now, if a ton of people in that group drop out because it's just too hard, who's left? Probably only the most athletic, most motivated people, right? So at the end of the study, if that group looks way healthier, was it because the program worked, or was it because only the super fit people were left to be measured? That's selective loss, and it makes your results completely misleading.
But the Barbie study was rock solid. They designed it carefully to avoid these kinds of traps. So, after all that meticulous control, the manipulation, the constant conditions, the balancing, what happened? What did they actually find?
Man, the results were just crystal clear. The girls who saw the neutral pictures and the more realistic Emma doll, their average body dissatisfaction score was 0. Zilch. They were content. But the group that saw the Barbie pictures, whoa, their average score was negative 2.76, which showed a real measurable desire to be thinner than they were.
And because the experiment was so well designed, because they had controlled for all those other explanations, the researchers could say something really powerful. This wasn't just a correlation. They could say that for these young girls, exposure to those Barbie images caused them to feel more dissatisfied with their own bodies.
So that's it, right? Case closed?
Well, in science, it's never really that simple. One study is a huge piece of the puzzle, for sure, but it's not the whole picture. True scientific confidence comes from seeing a result pop up again and again and again.
And this brings us to one of the most important ideas in all of science, replication. Replication is just what it sounds like. Other scientists in other labs repeat the experiment to see if they get the same result. It's the ultimate reality check. It's how we know if a finding is the real deal or if it was just a fluke.
When you step back, this whole system we've just walked through, manipulation, control, and balancing, it's not just for studying dolls. This logic is the fundamental engine that drives discovery in almost every field you can imagine, from developing new medicines to understanding how our brains work.
And that really is the big takeaway for you. Now you have the tools. The next time you see a headline that screams X causes Y, you can peek behind the curtain a little. You can ask, okay, but did they actually manipulate X? Did they control for everything else? Did they balance the groups? You can now ask the most important scientific question of all, how do they really know?